Welcome to welcome to week 8 of the TA session of Structure Analysis 1 taught by Professor Amit Shah. I am Trisha Chakraborty. I am one of the course teaching assistants. I am a first year PhD student at the Indian Institute of Science, Bangalore. We start with a brief recap of the previous weeks. First, the phase 1, the first 6 weeks were analysis of determinate structures, which is relatively easier and less complicated. So we started off with that. In week 1, we looked at types of internal forces, the four basic types of internal forces: bending moment, shear force, on which we have studied a lot, and there's also axial force and torsional moment. Then the common classification of elements like beam, frame, and truss elements, and the boundary conditions like hinge support, fixed support, roller support, and so on. And then we looked at structural indeterminacy and how to draw bending moment and shear force diagrams, which is one of the most important topics of this course. Then in week 2, we looked exclusively at trusses. We saw how to idealize truss as line elements or two force members that who can only take axial forces. Then we studied the stability of trusses and solving member force in a truss using two methods: the method of sections and the method of joints. And in week 3, we looked at the other kind of response of a structure. There are two major kinds of responses of a structure: the force response and the displacement response. In week 2, we looked at how to given a truss and the loading and boundary conditions, how to find the member forces inside on in its members. And in week 3, we looked at how to find the joint displacement. So for the tool for that is a principle of virtual work and the unit load method that helps us to determine displacement in trusses. In week 4, we moved on to beams and we did the same for beams, deflection of beams. There are several methods for that. The most direct one is the elastic curve equation method. Every beam or every structure is governed by every physical system basically is governed by a differential equation. And here, the differential equation of a beam is basically that d2y dx square is the moment, and by integrating that twice we get the deflection of the beam as a function of x, that if we vary x along the beam. Then there is another method called the moment area method, that is and the conjugate beam method. Both of these methods are basically variations or simplifications on the elastic curve method. We get the same solution from all these. These are moment area method and conjugate beam method. If we learn how to apply them case wise, we can reduce the time to we need to calculate the things. And in week 6, we looked at influence line diagrams, which is the basically to find out the maximum bending moment and shear force, or the maximum response of a structure under moving loads. That is, in general, when we find bending moment and shear force diagrams, or in general when we analyze, we take a fixed loading pattern, we take a certain loading pattern and calculate. But in real life, the loads applied on a structure will not be fixed, it can move along. That, for example, in a bridge, a car or a truck can move along its length. So influence line diagram, that is where they come into the picture. We saw the Muller-Breslau principle that gives a qualitative influence line diagram, and how to find absolute maximum bending moment and shear force under these point load series. A point load can be anything, that is, for example, a pedestrian walking, we can idealize it as a point load. A series of point loads is, for example, when a truck or a car moves, they have several sets of wheels. For example, a car has two sets of wheels. If it moves along the bridge, it will have two point loads moving. And uniformly distributed loads, as we saw that uniform distributed load we denote by W, it has the unit of Newton per meter. So when a set of length of uniformly distributed load moves along the structure, how we find the bending moment and shear force of that. Then we moved on to the phase 2 of this course, that is analysis of indeterminate structures. In week 7, the previous week, we reviewed the degree of structure indeterminacy, which we also will do today for trusses in particular. and introduction to force and displacement methods that are used to solve indeterminate structures. Basically, determinate structures can be solved very directly, right? We just solve the reaction forces from the equations of equilibrium, and then we can solve the entire structure. But in the indeterminate structures, there are more number of reactions than the number of equations we can get. So we need additional equations to solve those reactions. Hence, there are a lot of methods, a lot more methods and complicated methods to solve these structures. Introduction to force and displacement methods, which are two types of approaches. And we look at the Maxwell-Betty's reciprocal theorem, which is a very useful one, particularly for the competitive exams, the for MCQ questions. And method of consistent deformations, that is a force method. We began with force methods, and today we are going to look at method of consistent deformation applied to trusses. Before that, we will start with reviewing indeterminacy in trusses. Okay, so the structures that cannot be this is the definition of indeterminate structure. Basically, structures that cannot be analyzed using statics or equations of equilibrium only, because they have more number of unknown reactions than the number of equations of equilibrium. So the degree of if the degree of indeterminacy is one or more than one, we will call it an indeterminate structures, and they require other material properties to be solved. In general, when we are solving for bending moment or shear force diagram, we do not need for example, the Young's modulus or the Poisson's ratio. You would have learned about these properties in class 11 and 12 at least. Young's modulus is the proportionality constant between stress and strain, and Poisson's ratio is another material parameter that is fixed for a particular material. For bending moment shear force diagram, we didn't need these properties, but for to solve these structural and indeterminate problems, we will need those to, because we need some additional criteria. We have, suppose we have four reactions and only three equations of equilibrium. We need some other criteria to solve the reactions, because till we solve the reactions, we cannot solve the internal forces and things. External indeterminacy is the total number of independent support reactions minus total number of available equations of static equilibrium. Now, in two dimensions, the number of available static equilibrium equations are three. One is that the total summation of forces along x-axis should be zero, the summation of forces along y-axis should be zero, and the out of plane or into the plane moment, that is mz, we can say mz should be zero about any point in the structure. That is those are the three equations we have in 2D. And in 3D we have six equations, six equilibrium equations, because we have three translational directions x, y, and z, and we have three rotational directions mx, my, and mz. So we have six equations of equilibrium, and the number of independent support reactions, we know how to find that. For example, if there is a fixed support in two-dimensional plane, it provides us three reactions. If in 2D, if we have a fixed support, it will provide us with three reactions. It will restrict the translation in x direction, translation in y direction, and the rotation in the z direction. However, a fixed support, it will look the same. If it is drawn in 3D also, it will look the same. A fixed support in a three-dimensional plane with three-dimensional zone, that is what we see in real life, that provides a six support. Okay, fixed means there is the all 6 degrees of freedom, and or whatever the number of degrees of freedom be at that point should be restrained. So a fixed support in three dimension means the translation in fx, in x direction, y direction, and z direction or all three are restricted, and the moments in all the rotation in all three directions are restricted. So in two dimension, if you have a fixed support, the number of independent support reactions from that support will be three. But but in but in three dimensions, if you have fixed support, the number of independent support reactions from that support will be six. So that is how. And similarly for hinge support also, you know that in 2D we have seen how hinge supports act. Hinge support are supposed to give two reactions, one is in the x direction, one is in the y direction. But if a hinge support is present in three dimensions, it gives three reactions. I mean, it restricts the translation in all three directions, x, y, and z. So according to that, we can find out the external indeterminacy. And internal indeterminacy is total number of internal reactions minus available equations of equilibrium. And the degree of structural indeterminacy is summing these two. We will look at some examples today, some These examples we have already looked at. This is a cantilever beam that has the fixed support gives three reactions, and we have three equations of equilibrium in two dimensions. So this is a determinate structure. This prop cantilever has again it has three supports from the fixed support and one support at this one at this roller support. There is a reaction in the y direction. So there are total four reactions and three equations of equilibrium. So it is this structure is 1 degree indeterminate because 4 minus 3, that is how we get it. This truss, this frame is a 2D frame. So in a 2D in 2D frame 2D plane, this these things fixed support give three reactions each. So there are six reactions and three equations of equilibrium. So we have this the structure is 3 degree indeterminate. And this these are hinge supports. Hinge supports give two reactions, x direction, y direction, x direction, y direction. So we have four unknowns and three equations of equilibrium. So this structure is 1 degree indeterminate. Now these are the rules. I mean, these are some formula that we use to find out indeterminacy, degree of indeterminacy in the truss. So the first step when you are given a structure is you have to find out its degree of indeterminacy, because if it is a determinate structure you can solve it directly. You have you can just solve the support reactions directly and go into the problem. But if it is indeterminate, we will have to employ the other methods we are going to learn now, or we learned in last class in the last week in week 7. We learned how to solve indeterminate beams using method of consistent deformation. This class we are going to looking at we are going to look at how we solve indeterminate trusses, and week 9 looks at how to solve indeterminate frames. So this is the first rule. I mean, the first approach to the first step to find out degree of indeterminacy. DS is this DS is the degree of total indeterminacy. Okay. So total unknown forces external plus internal minus total equation of equilibrium available. So this is, we say that for a truss, M is a number of members. We know that in a truss, every member is a two force member. That means it can only be under axial tension or axial compression. That corresponds to one value. In if there is if every member of the truss has one internal force, so the number of internal forces is the number of members in a truss. That is not how it works in a beam. In a beam, if in a beam you cannot say there is only one unknown, because in a beam the shear force and bending moment all vary along the section of the beam. So this formula is only applicable for trusses. M is the number of members and the number of internal forces, internal reactions. I mean, you can say internal forces. RE is the number of external reactions. External reactions means like these. If this was a truss, I mean, in a truss, these hinge support, fixed support, roller support, these would be the number of external reactions. And J is the number of joints in a truss. So number of joints in, for example, just for example, this has 1 2 3 4 joints, so J will be 4. And if DS equal to 0, the truss is statically determinate. If DS is greater than 0, the truss is statically indeterminate, because it has more number of unknowns than reactions. And if DS is less than 0, the truss is unstable. See, what does instability mean? If you have less number of reactions than less number of unknowns than the number of equilibrium equation, that will inevitably mean there is some kind of instability. For example, consider a truss that has there are three equations of equilibrium. Suppose it has just two reaction forces. Suppose there is a truss and it is supported by two rollers on each side. Then if you apply horizontal force, there will be no one to resist it, no reaction force to resist it, so the truss will move in the horizontal direction, so it is unstable. Now for example, there is a truss where there is only one hinge support. If there is one hinge support, it gives us two reactions in x direction and y direction. So it can resist translation in x and y directions. But if you give a horizontal force, for example, suppose this is one leg of a truss, this is another, and this is another. Suppose just a triangular truss, there is one hinge support. If you put a force in this direction, the truss will rotate in this direction, so it is rotationally unstable. So basically, the number of unknowns being lesser than the total number of equations is a shortcut to understand that there is some kind of instability. Now if you study the kinds of support reactions, you can understand in which sense it is unstable. Like, and now if the same truss that was supported in two rollers in x direction, the kind we in the y direction, the kind we imagine rollers to be oriented in this direction. So if you put a horizontal force, it will move. Now suppose there is a truss where there are two rollers in this direction, along the x direction. Then if you put a force in the y direction, it will move downwards. So in any way, there has to be some kind of instability. So when ds is less than 0, that any structure is statically unstable, that we do not consider, because building unstable structures is never in question. If there is instability, it is not a valid structure. We call it a mechanism. Now if a structure is statically determinate, it is a valid structure. It is easiest to analyze, but in real life we do not actually work with the determinate structures. All the buildings or bridges or anything you see around you are several degrees indeterminate, because indeterminacy makes a structure safer. It means that suppose one support reaction fails or one member fails, it means that there will still be stability in the in the structure. So for example, if an earthquake comes or something, if the if the structure is, if for a determinate structure an earthquake comes, if any one mode fails, if one support reaction fails, the entire structure will collapse. But in if it is an indeterminate structure, suppose one reaction fails, suppose here this prop cantilever, suppose this prop fails, suppose this fails, so it can no longer resist this, but the structure will still be stable till so long as this fixed support is there. So you will get some warning time in case the structure is about to collapse. If it collapse one, if the support reactions or anything collapse one by one, you will get warning time to evacuate and all that. And in general, if it is not, if it is suppose a short, if the duration of the earthquake is short, it can also be the structure will not collapse because a few modes fail, but the other modes are enough to keep the structure stable. Then you will of course go for repair later on. But of course, the first step is not to make the structure collapse at once, because if one failure makes a structure collapse, it is too unsafe. Especially in civil engineering, we work with people's lives, right? So in civil engineering, safety is a very very important governing criteria during design. But again, at the same time, economy is also important. We cannot just keep making it safer and safer and safer, because the cost of construction will also increase. So design is basically a balance between safety and cost, but we have to be safe enough. That is the most important thing. And in space, now we move on. This was plain truss, 2D truss, and we move on to space truss here. This, see, basically why is this 2j coming here? This in 2D truss, this 2j is coming here because imagine how you solve a truss. When we solve a truss by the method of joints, at each joint we have two reactions. We have one fx, sigma fx equal to 0 and sigma fy equal to 0. So that is basically we will get 2j number of equations. I know the equations of overall equilibrium will be 3. That is different. Here the total number of equations, if you go inside, there will be at every joint you will get two independent equations. So the total number of equations will be 2j, and the total unknowns will be m plus re. And similarly in a space truss, there will be even in a 3D truss. See, what is a space truss? It is a truss that is oriented in the three dimensions. But suppose there is one member that is neither along x-axis or y-axis. That is not in the xy plane. That is in the xyz plane. It can be, I mean, not plane, space. It can be oriented any direction. But since it is a truss, that member will still be a two-force member. That is, it only has an axial force along its direction of orientation. It cannot have more than one forces inside it. Every member. So the number of internal unknowns is still m. There is the number of members, and the number of external reactions is re. Take that accordingly. Like for example, if there is a, as I said, if there is a fixed support in a 2D truss, you will take three unknowns. But if there is a fixed support in a 3D truss, you have to take six unknowns for that. So so m plus re minus 3j, because here the number of joints, if it is j, you have three equations at each joint: sigma fx equal to 0, sigma fy equal to 0, and sigma fz equal to 0. And that is, I mean, we have not solved space truss. I don't think that is included in your syllabus, actually solving space trusses, because there will be, I mean, a lot of trouble. Because in 2D trusses, if the truss is oriented in some direction, we have the theta and we can take the cos theta sin theta components. But in a 3D truss, we have to take the direction cosines and all that. I think that is not included, but the indeterminacy part can come. It often comes, in fact, in gate and exams like that. I think gate ESC, these are quite common. These are some examples we'll look at. So this is a 2D truss. We have to find the degree of static indeterminacy. How many members are there? Okay, I think earlier I said there are four joints, but actually not. This is also a joint. So one, two, three, four, five. J is five here, and the number of external reactions, that is that Re, these are all hinge support, and hinge supports in 2D have two gives us two reactions. So there are six total unknown reactions. Re is, see, this is the formula we are studying right now. So Re is 6, and there are 1, 2, 3, 4, 5, 6, 7 members. So M is 7, Re is 6, and J is 5. So we see that it is 3-degree indeterminate. This is a direct formula you can apply, and this is the one most people seem to prefer. There is another approach here where actually you can calculate the degree of of the degree of internal indeterminacy and external indeterminacy, and then add the two. So see here, the degree of external indeterminacy is simply what we generally perceive as indeterminacy, that Re minus 3. That is total number of external reactions minus 3. And for 2D it will always be 3, and for 3D it will be 6. So Re here is 6 and this is 3, so 6 minus 3 is 3. And degree of internal indeterminacy has this formula. You can see that these this formula and this formula actually add up to this formula only, but m minus 2j plus 3, or m minus 2j minus 3 inside brackets. So from here we get that degree of internal indeterminacy is 0. So what does this mean basically? Degree of internal indeterminacy being 0 means that even if it is externally indeterminate, once you have the external reactions, you can solve the internal forces without any trouble. But suppose there was internal indeterminacy as well as external indeterminacy, then even if you have somehow managed to find out the external supports, you still cannot solve the truss, all the member forces of the truss. For that, you have to apply some extra methods that which I'll show later on in this class. And adding this DSE and DSI, we get 3, that is the degree of static indeterminacy. You can remember, basically what I do is I remember this formula. This is the total degree of indeterminacy, and this DSE, degree of external indeterminacy, is very logical. Like if you forget whatever is inside, to degree of external indeterminacy means whatever has to do with the reactions. So there is a total number of reactions minus 3. So once you have the DS and the DSE, you can find out the DSI by simply subtracting the two. And you may be asked, you may be asked to find out degree of internal indeterminacy as well in exams. So keep in mind, remember at least two of these. What is the total degree of static indeterminacy, both internal and external, of this? This has, see, the number of joints, even if they are not marked in circles, you can see the number of joints. That, okay, there is one thing, there's another thing, that if two members are crossing over like this, unless there is a circle made here, you will not assume this as a joint. You will assume these two members are like this, they are overlapping members, but they are not separate members. Like this part and this part are continuation of the same member. So these two are one. Inside there are basically four cross members, not eight. So there are seven joints: one, two, three, four, five, six, and 7. And the number of members you can see: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And the number of reaction forces, they are both hinge supports. So there is 2 plus 2, 4. So from this, the overall formula, you find m plus Re minus 2j, you get 3. And now you see the degree of external indeterminacy. You can see that there are 4 reaction forces and there are 3 equations of equilibrium. So it is 1 degree externally indeterminate, and the rest of the indeterminacy comes from internal. So 3 minus 1 will be 2. So DSI is 2, DSE is 1. Now there is another thing, that if there is an internal hinge, there is, the formula is kind of modified a little bit. This this m is 5. See, if there is a hinge support, this member doesn't break. Okay, this is one member, this is one member, this is, okay, no. If there is a hinge as well, you have to take it as two different members. So the number of members here is 5. 1, 2, 3, 4, 5. Internal hinge or external hinge or roller, whatever is there, you cannot consider this as a single member. So m is 5, and the number of joints is 6. 1, 2, 3, 4, 5, 6. Both the internal hinge and the external hinge are joints. And the number of reactions, see, there are 3 fixed supports in a 2D truss. The 3 fixed supports are, all the fixed supports give 3 reactions each, and this is a roller support that gives the reaction in this direction. So there are total 10 external reactions, and there is also one internal unknown. This R is the, I think it's R, yes. RR is whatever you call it. It is there is one unknown here at the hinge as well, because there will be a load transfer between the hinge. So this this RR is 1, and this is basically this is a frame. So the formula is a little modified. The formula for frame is 3m plus 2e minus 3j minus 2r. This is a formula for 2D frame. For 3D frame there will be 6. This 3m, why is the member multiplied by 3? Because the total number of unknowns in a frame. What is a frame member defined as? A frame has axial force, it has shear force, and it has moment. So in a frame, there are three. For each member, there are three unknowns, and in a beam, for each member, there are two unknowns: the bending moment and the shear force. But in a truss, there is only the axial force. So basically, this is the formula: 3m plus re, and each joint there are three equations: f sigma fx equal to 0, sigma fy equal to 0, and also moment equal to 0. Now this moment does not come in truss, because in truss every moment is a two force member. So every joint is basically acts as an internal hinge where the moment will automatically be 0. So in a truss we say m plus re minus 2j. Here we say 3m plus re minus 3j, and you have also to subtract this, because at every internal hinge, you get an additional equation. Remember, when we I think in week 1 or week 2, when we were working with bending moment and shear force diagrams, at internal hinge we get an extra equation. So this is subtracted. The total number of unknowns minus the total number of equations we get as 6, and from this formula we get the degree of external indeterminacy remains the same, whether it is truss or a beam or a frame structure. The concept of external indeterminacy will always remain the same. The number of external support reactions is 10, and there are three internal, three equations of equilibrium. So the degree of external indeterminacy is 7, and here the degree of internal indeterminacy is -1. This basically means that, if see, a degree of internal indeterminacy cannot actually be -1. So if that it is -1, it means it is an unstable structure. This is another frame. Here also we have an internal hinge. Here we see the number of joints: 1, 2, 3, 4, 5, 6, 7. There are 1, 2, 3, 4, 5, 6, 7, and this internal hinge. So there are 8 joints. There are 11 members: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. So M is 11, J is 8, and the number of external reactions is, there is one hinge and one roller. So you can basically see that it is externally determinate structure. If you forget about what is inside, you can solve the external support reactions at least, because you have three equations of equilibrium and three unknown support reactions. So DSE is Re minus 3 equal to 0, and the degree of total indeterminacy from this formula is 3 into 11 plus 3 minus 3 into 8 minus 1, because there is one internal hinge, and 11 is the degree of total indeterminacy, and 11 is the degree of internal indeterminacy here as well. 3D frame, I think we can skip for now, because 3D frame, it's it's unlikely to be asked. Maybe we can look at this. This is the formula. As I said, in a 3D frame, each frame member has 6 inherent unknowns. It can have an axial force, it can have a bending moment. Suppose you imagine a member that is oriented around the x-axis. Okay, so it can have a force along x-axis, which is called the axial force. It can have a force along the y-axis, which is called the shear force, and it can also have an force along the z-axis, which is also a shear force, because basically shear force means any force that is not along the axis of the beam. I mean the components that is perpendicular to the axis of the beam. So the axis of the beam is x-axis. Then there are two other directions perpendicular to it, y and z, and they are both there are two shear forces in those two directions. In 2D, if the frame was 2D, then we would not consider the z direction force, right? Because we are not considering the z direction at all. And then there are three kinds of moments as well. The moment along x-axis, where the sense is along x-axis, it is a torsional moment basically. You imagine a frame that is being twisted along its own axis, it is called torsion. And then there are two bending moments. One is the mz, and one is the my. So in a 3D truss, in a 3D frame element, there are 6 unknowns corresponding to each member: 3 translational, 3 rotational. So the number of unknowns, internal unknowns, is 6m plus Re. That again it remains the same. Re is always the total number of external reactions minus the number of equilibrium equations, and 6m plus Re minus 6J. Here each joint has 6 reactions, because in three translational you have to write sigma fx equal to 0, sigma fy equal to 0, sigma fz equal to 0, and you also have to balance the moments at in each sense. Sigma my equal to 0, sigma mz equal to 0, and sigma mx equal to 0. So 6m plus Re minus 6J minus Rr. This remains, I mean, the number of internal hinges you have to subtract from the number of unknowns. So here we have 9 members: 1, 2, 3, 4, 5, 5, 6, 7, and 8, 9. These are two different members. Okay, if there is an internal hinge, you have to take two different members. So there are 9 members, and these two are fixed supports. At fixed supports for a 3D structure, we have 6 unknowns. So 6 into 2, 12, and there are two hinge supports, so there are three each, because a hinge support in 3D plane gives you 3 reactions. So we have 18 unknown external reactions. We have 6 joints: 1, 2, 3, 4, 5, 6, 7. Sorry, you have nine joints: 1, 2, 3, 4, 5, 6, 7, 8, and this internal hinge 9. So, and there are, and at this internal hinge, see R here, in an internal hinge in a 2D plane gives you one extra reaction, but this you are not supposed to know from before. This is the first time we are encountering a internal hinge in a 3D plane that gives you 3 external reactions. They are not important for problem solving, that won't be given in a undergraduate structure analysis course, but just for your information. And an internal hinge in a 3D plane gives us 3 extra reactions, so we have to subtract this 3 from here, from this. Rr is equal to 3 here, so the degree of total indeterminacy is 15. Degree of external indeterminacy is, as always, the Re is 6 plus 6 plus 3 plus 3 is, that is 18, and the total number of equation equilibriums in 3D plane is 6. 3D space is 6, so the degree of external indeterminacy is 12, and the total one is 15. So we can see that the degree of internal indeterminacy is 3 here. This is another, I mean, a plane. This is again a plane frame. The number of external reactions: 1, 2, 3, 4. There are 4 fixed supports, so there are 12 unknown reactions and 3 equations of equilibrium, so DSE is 9. And this is just the way we were working earlier. We can find out the number of members and use the formula. Okay, we'll look at these later, because these are basically frames, and today we are looking at trusses. This force compatibility or flexibility method that we touched upon the last class, I'll brush through the concept of force and the difference between force and displacement method, and then move on to how to apply it on a truss. Okay, so redundant forces in the or the compatibility or the flexibility method. The redundant forces. What are the redundant forces again? The number of every. I mean, suppose there are 4 unknown support reactions, and you have 3 equations of equilibrium. So we have one support reaction that we could do without. Like for the stability of structure, we could take away one support reaction and still call it a stable structure. So, for example, in this, just for example, to take this prop cantilever, here this vertical force, if you can call this a redundant force, because if you suppose it wasn't there, this would still be a proper cantilever beam, a stable cantilever beam. So you can take this RC as a redundant force. Again, you could also take this, for example, if this was instead of a fixed support, if this was a hinge support and one roller support, that would be a stable simply supported beam. So you can also consider the the moment at A, as a redundant force. That is what we call the redundant force. So here we have to take the redundant forces are chosen as unknowns, and additional equations are obtained by considering the geometric conditions imposed on the deformation of the structure. The conditions are known as compatibility conditions. And there are some, okay, the redundant forces, the number of redundant forces to be taken as unknown is equal to the degree of static indeterminacy. If the structure is 1 degree indeterminate, you have to take one force or moment as a redundant force. If it is 3 degree indeterminate, you have to choose 3 forces or 3 combination of forces and moments that are redundant forces, and that will be the number of unknowns to be solved using the compatibility conditions, because the number of equations equal to the equations of equilibrium you can already solve. So 3 forces or moments by default you can solve using equilibrium equations, and the remaining forces, the redundant forces, you have to solve using these compatibility conditions. And there are several force or flexibility methods. One is the method of consistent deformation. It is the most commonly used one that we used in beams for week 7. There is a virtual work or unit load method, strain energy method, method of minimum potential energy, and flexibility matrix method. All these are okay, but I think the Professor Amit Shah, sir did cover some of these methods, but mostly the method of consistent deformation is the one most commonly asked and most commonly used as well. And the concept of displacement or equilibrium or stiffness methods is, here the displacements of joints are taken as unknowns, and equations of equilibrium are expressed in terms of these displacements and internal loads, and these equations are solved to give the actual joint displacement from which redundant forces can be calculated. Basically, in the previous one, we take the forces as unknowns, and here we take the displacements as unknowns, and that is how approaches get their name. And there is a moment distribution method, slope deflection method, and the stiffness matrix method. All three of these are very important for this course, and week 10, 11, and 12 cover each of these methods. I think slope deflection in week 10, week 11 covers moment distribution, and the final week is a stiffness matrix method. These are the summarized differences between the two methods, two approaches basically. In force method, unknowns are taken as the internal member forces or reactions. In displacement method, unknowns are taken as joint displacement. To find unknowns, here we write the compatibility conditions, and the number of equations required is degree of static indeterminacy. As I said, the number of extra equations that you need to solve the external support reactions. And here, to find the unknowns, joint equilibrium conditions are written, and the number of equations needed is degree of kinematic indeterminacy. That is not the same as static indeterminacy, what we just looked at. That is the degree of static indeterminacy. It has nothing to do with kinematic indeterminacy. We will look at that later when we start the displacement methods. And of course, whatever, if the degree of static indeterminacy is lesser than the degree of kinematic indeterminacy, we will prefer the force method, because it will have lesser number of unknowns and lesser number of equations to solve. And this method is suitable when degree of static indeterminacy is greater than degree of kinematic indeterminacy. Now we move on to the analysis of indeterminate truss by method of consistent deformation. First, we start with an example. First, what we want to do, this is a first. Let us check whether this truss is indeterminate or not. See here, the number of members here, because the number of external reactions is 1, 2, and 3. So externally this truss is determinate, but internally, let's say how many members are there? 1, 2, 3, 4, 5, 6. There are 6 members, and there are 4 joints. 6 members plus the number of external reactions. So 6 plus 3, we have 9 unknowns, and we have 4 joints. So 4 into 2, 8 reactions. So this truss is 1 degree statically indeterminate, and that is basically an internal indeterminacy. And why is and now let us try to visualize why this is internally indeterminate, because externally it is determinate. We can see there are 3 support reactions which we can solve externally, but internally it is indeterminate. That means, suppose there are 2 members here, suppose you take away 1 member, suppose 1 member wasn't here, it was a truss with 5 members, it would still be a stable truss. That is what is meant by indeterminacy of any kind. You can take away a support reaction or a member or something, and the truss will still be stable. But if you take away another member, suppose you take away both the diagonal members, then this truss will no longer be stable. It will become a mechanism. It can collapse into itself. So remember this. This is a very common advice, a very simple kind of shortcut, that in a truss there has to be triangles. You can have no rectangular section. Like, if you see a rectangle in a truss, it means it is unstable. Okay, so the minimum you have to do is form a triangle. So even if you take away one of these members, there will still be 2 triangles, so the truss will still be stable. So this is 1 degree internally indeterminate. And what do we want? We did want to determine the force in member AC of the truss, or basically we can find out the force in every member of the truss. And AE, that is area, and this area, cross sectional area, and E, the Young's modulus, is same for all members. Now, I had mentioned earlier that in for determinate structures, to find out the member forces, you do not need geometric or material properties. So you need the length, of course, but you do not need the A or the E. But here you need that. This is 1 degree indeterminate. Now the principle of superposition. This is only valid for linear elastic structures, but all structures we are looking at right now are linear elastic, so you don't have to worry about that. And the force in member AC is to be determined. So member AC is chosen as redundant. Here, any one member you could have taken as redundant. We chose AC as redundant. This requires cutting this member so that it cannot sustain a force, making the structurally making the truss structurally determinate and stable. So see, we divide this into two parts. One where this member is not here. Suppose this member is not here, then it will be a determinate truss, and here we will apply a redundant force FAC. I mean, in the first part, see the primary structure, just like in beam, in the primary structure, what we do is we remove the redundant force or the redundant force or the internal member force, whatever we remove it. We make it a determinate structure, and we keep the applied load. Here 400 pound was applied, we will apply 400 pound here. And the extra structure, the other structure that will linearly superimpose with this primary structure to form the actual structure, what we do is we remove the applied forces. We forget about all the forces that were applied. We keep the boundary conditions intact, like with this hinge and roller we will keep here. And in this member that we have taken redundant, we will apply an FAC that is yet to be determined. We do not know its value. So this basically, this is not a member here. This is basically force applied as if it was a member. Like there are two FAC is applied at this joint. FAC is at this joint, and FAC force is applied like this. And at this joint, and FAC force is applied like this. You can see that since these two forces are acting along the same direction, it does not affect the external equilibrium. It will cancel each other out. So the primary structure and the redundant structure. Now the compatibility equation is with reference to member AC. We require the relative displacement delta AC, which occurs at the ends of the cut member AC due to this load, plus the relative displacement FAC small AC. These I mean I will explain these terms. Basically the compatibility, what the compatibility condition says is that the total elongation or shortening, since this member is not these two members are joined, these two are joined, the total deflection, the total deflection in this member, the total displacement in this member should be zero. There will be two contribution, one from the primary structure, one from the redundant structure, that should add up to zero. So see what if the flexibility coefficient, that is, I mean basically flexibility coefficient means it has to do with the unit load method, what we did in the unit load method while finding displacement in trusses. See, this is a determinate, these two are determinate trusses. So if you want to find out the displacement of the joints in this truss, you can use a unit load method. So this small FACAC is the displacement, this here is the elongation of this member due to a unit load applied here. So that is a small f, and the capital F is the magnitude of force in AC which we do not yet know. So if the unit load was applied here, we will get certain elongation or displacement in this truss member, that will be small f ACAC, and that will be by the principle of linear superposition. It means that if you apply a unit load in a structure and you get a certain displacement delta, if you apply a force F in the same pattern, you will get a displacement of F into delta. That is the principle of linear superposition. So capital F into small f plus this, now this was from contribution from this structure, and the contribution from this structure is delta AC. They should add up to zero. Both these sigma AC and this small f shape would be calculated by the method of virtual work. So basically, in the method of virtual work, what do? We need to drop. This is the formula we used here. N is the capital N is the load applied. L is the length of the member. The length of yes, this is 8. So if this is 8 and this is 6, then we know this theta. We can find out the length of this member. So this L into zero point 0.8 is the length of this member. This 400 is the applied load, and this we have to add over all the members, right? So this the force in this the force developed in each member into the length of that member by AE of that member. Here AE has been said to be constant, so we have to add. See this, in this structure there are, in this determinant structure there are 6 members. So here you put a, for this you put a 0 here, because we are assuming that it has no force right now, and we will solve the delta AC as we are getting it like this using the using the virtual work method. And similarly, you if you take this structure, this is also a determinate structure because we are assuming the load here, force here to be 1. Here we again apply the same formula. We are writing n square here because there is no, we are writing n square here because everything here is in the terms of one force, right? There is no, I mean, applied load is unit. And from here we will get this thing. This is similar. I'm not going into these details because it has been covered in week 3, I think, when we solved the displacement, joint displacement of truss using of determinate trusses. Now here, these are the primary structure and the redundant structure are basically two determinate trusses that you are solving. From that, if you get the small f and the delta, then you will use this equation. This is the compatibility equation. Basically says that the contribution from this and the contribution from this should add up to 0, and the contribution from the first part is what we calculated this. And this is the contribution. If that member force AC was 1, this would be the deformation. But since this FACs are unknown, which we don't know what the member force is, so if we write, this is basically the equation, the delta plus small f into capital F is 0, and here we get FAC as 324. Since the numerical result is positive, AC is subject to tension as assumed. We originally assumed that the AC is under tension. And once you have this member force, once you have this member force, you can forget there is a member here. You can just put two equivalent forces, and then then it becomes an externally and internally determinate structure. So after that, you can calculate all the responses as we have studied earlier for determinate trusses. This is the, I mean, the basic steps. First we determine the degree of indeterminacy. What we just did. The redundant is the support reactions and or the forces in bars. So what? How many? See, if the degree of external indeterminacy is 2, you have to take 2 support reactions as redundant forces. If there is no internal indeterminacy, you don't have to take any member force as redundant force. But basically, the number of internal indeterminacy is the number of member forces that you have to take as redundant. And similarly, the degree of external indeterminacy is the number of support reactions you have to take as redundant. So total number of redundant forces is equal to the degree of indeterminacy. And now see, suppose you have degree of external indeterminacy as 2 and internal as 1. Total is 3. Total degree of indeterminacy is 3. Then you cannot take 3 support reactions as unknown, okay? Because if a structure is externally indeterminate to the order of 2, if you take away two forces, it will become just stable. And if you take away another external support reaction, it will become an unstable structure. So you have to take it correspondingly. That you have to find out the degree of external indeterminacy, internal indeterminacy, and according to that, you have to choose your redundant unknowns, that how many support reactions you will choose or how many member forces you will choose. And we will follow the similar steps as we used in beams, following compatibility equations, that this delta 1 0 plus small delta 1 1 x1 plus this is if it is 2 degree redundant, plus delta 1 2 x2 is 0. Settlement, see, actually settlement is, I mean, it will come into the picture in later weeks or probably not in this course. But it's like, we assume that every support is completely rigid. For example, in a roller support, we assume that there can be no deformation in the y direction. But there are also some kinds of supports, partly yielding supports. They yield to some extent. Suppose it says that there's a roller support, it will give a vertical reaction force, but it can settle by 1 millimeter. So then the approach will slightly change, that we are not looking at right now, but just this is just a general piece of information. These are the compatibility equation we will see basically. At here, delta 1 0 is SU1 L by EA, that is the sigma. And basically these, see, S is the primary truss and U1 is the, I mean, the redundant truss where we only apply the unit load. So S is the response of each member, I mean the force in each member of the primary truss, and U1 is the force in each member in the unit, in that unit load truss. So this is basically the contribution. You can see that these two, this term and this term we have already encountered. This force in the primary truss into the force in a unit loaded truss into length by EA, summing over that we get the displacement. Already we have studied this same from the unit load method. And see, these contributions are basically if there is temperature elongation, and this if there is misfit or something, these two terms you can temporarily ignore. So delta 10 is SU1 L1 by EA, summing over that. Delta 20 is SU2 L by EA. Now what is this U2? We said that if this truss is too redundant, then there will be two redundant trusses. There will be one primary structure, one truss and another truss. So there will be total three trusses, SU1 and U2. And here delta 1 is within that unit, within the one of the unit trusses. When we will consider only this u1, that is this formula, delta 11 is u1 square L by EA, delta 22 is u2 square L by EA, and this coefficient, this 2 1 2 1 2 1 is equal to each other, and that is delta u1 u2 L by EA. One example will make it clear. This is a truss. See, this has 1 2 3 4. There are four external reactions, and internally you can see that how many joints are there. 1 2 3 4 5. There are five joints. There are 1 2 3 4 5 6 7 members and four external support reactions. So 7 plus 4 is 11, minus 2 into 5, so 10. So basically there is no internal indeterminacy in this structure. There are four support reactions, and we have three equations of equilibrium. So it is 1 degree externally indeterminate, and internally it is a determinate structure. So what will we do? We will choose any of these forces, any of the external reaction forces as a redundant force. Here we choose as this support. So we remove, so in the primary structure we remove this support. We draw this truss, and in this U1 there will be only be U1 here. There will not be any U2 because there is only 1 degree of indeterminacy. We will put a unit load here, a unit load in this direction. I mean, we are assuming the force will be in this direction. So we are putting a 1 kilonewton here, and we have removed this 40 kilonewton. You remember that in a primary truss we put the original loading, but in this unit truss we remove the original loading and just put a unit load in place of the redundant force. So then you have to solve these two trusses. These are both determinate trusses. You can solve these two trusses. This is the length of each member. S is the system solved. This system has been solved. We can solve the using method of joints or method of sections. We can solve the member force in each of the seven members. So this here we have solved, and similarly this other structure. This is also a determinate structure. You can solve using any of the methods you have solved. So you have got the U1 system of forces and the S system of forces, and you have SUL. Since AE is constant above all, we have assumed. So SU1L will be this, and U1 square L is this. And what will be the compatibility condition? Basically, delta 10 is this part. SUL, so sigma of SUL by AE, and delta 11 is this sigma by AE. And this was the formula we were supposed to use. X1 is the unknown. Okay, X1 is the unknown reaction force. Why are we using this formula? It means that since this support cannot be displaced, there is displacement in this truss, in the primary truss at point C. That is this part. This delta 10 is the displacement of point C in the primary truss, and this delta 11 is the displacement of this point due to this unit loading. And but there is not going to be a unit loading here necessarily, right? There will be some RC that is unknown to us. So RC into this delta 11 plus this capital delta 10 has to be 0 according to compatibility conditions. So we get this X1 as our unknown as minus 6.63. So this means that this reaction at Cy will be 6.60 in the upward direction. Why in the upward direction? Because when we put a 1 kilonewton downwards, we were inherently assuming that the force at this point is downwards. Since we got a negative value, it is upwards, and the remaining reactions can be found by applying equilibrium equations. Now see, there was one extra redundant force due to which we were unable to solve because there were four unknowns and three support reactions. Sorry, there were four unknowns and three equations of equilibrium. Now, once you have this force, once you have one of the reaction forces, you can just treat it as an applied force. You can forget about the support and treat it as this applied force of 6.16 in the upward direction. Then you can solve this truss, because then you can solve these support reactions, because there are three unknowns and three equations. So there should be no problem, and once you have solved these reactions, you can also find all the member forces. Now this is a truss with, see, this, in this truss there is some temperature increase and some member fits. That part we will ignore for now, because I don't think that is properly included in the syllabus. But this truss interestingly has external indeterminacy as well as internal indeterminacy. You see, this has one hinge and another hinge support. So there are four external reactions, three equations. So it is 1 degree externally indeterminate. And internally also, you can, you can of course go into the calculations and find it out, but you can just by seeing it. With the minimum requirement in a truss is to form triangles. So whenever you see this cross member sort of thing, and there are, if you, even if you take away one member, there will still be triangles. So basically one of these members is also redundant. So it is 1 degree externally indeterminate, 1 degree internally indeterminate. So we have to build two unit loading structures and one primary structure. What in the primary structure, it has to be completely determinate. So we take away one extra member. We have taken away this member. So we have drawn it like this, and we have also taken away this vertical reaction, because we have to make it externally determinate as well. We have let the hinge remain. We have converted this hinge into a roller. That is, we have assumed that there is, we have taken this vertical support reaction as an external force, as a redundant force, and we have taken away this member. So this is a completely determinate truss, the primary truss, which has the applied loading. There was 80 kilonewton here. There is still an 80 kilonewton here, and the boundary conditions. Then in our first unit truss, this U1, we still forget about this member. This member is not here, but for this support, there was a vertical support here. So we take a 1 kilonewton. You can take it in any direction. You can take it in any direction. Just assumption is, assumption here is the force is downwards. If you get negative value, you will put it upwards. And then in the U2 unit truss, we ignore this force, but we take this member force. We assume it as a unit load, like we did in the unit load method. So we have three trusses. We have three determinate trusses. The primary truss, U1 and U2. Now what we have to do is solve all the trusses completely. It is a hectic process. Like it is a 1, 2, 3, 4, 5, 6, 7 member truss. You have to solve it 3 times with completely different loading patterns. So you have to solve it 3 times independently, and you can write down the forces here. And here you basically you follow this formula, that delta 110 is this this formula. As I said, this delta 10 is SU1 L by EA, and delta 20 is SU2 L sigma by EA. So by using this form, if you put all this, see, now you know the S system of forces, U1 and U2 system of forces, you know length in each member and EA of each member. So basically you get two equations in two unknowns. X1 and X2 are the two unknowns. And what do these unknowns represent here? Since U1 is corresponding to this load, so X1 is basically the vertical support reaction at E. And since U2 is corresponding to this member force, X2 is the member force in this member BC. So using the two formulas, these are two you end up with. So you can solve, see here, this these temperature and misfit things are used there. Them I'm ignoring. If suppose there was no temperature and this thing given, the delta 110 would simply be SU1 L by EA sigma, and the delta 20 also will be simply SU2 L by EA sigma, and the delta 1222 and 112, you just saw the formula. From basically you have to solve this table, and which parts are you solving? L is already given, or you may have to solve it using geometry. And this S system, U1 system and U2 system you solved. This part is what you have to solve, and after that all these you have to multiply and add, and then find out this. So these are two equations we are getting in x1 and x2. Simultaneously, you can solve x1, x2 as these. So we get that x1 is x62. That means that means this truss has a downwards direction of 62, because we assumed it to be downwards 1 kilonewton. Since it has come to be positive, there is a downwards direction of 62, and x2 is 135 kilonewton. So this member force is 135 kilonewton. Now that you have these two, this is basically a primer. This is basically, you can treated as a primary truss with a force here, as I mean 135 in this direction, and a 62 downwards, and it is again a determinate truss. So you can solve the support reactions, you can solve all the member forces using method of sections or method of joints or anything, and you can solve the entire truss entirely. So summing up, what do we basically do in the force method? We first calculate the degree of indeterminacy. Correspondingly, we take choose some redundant forces, some member forces or support reactions, and then we solve them using compatibility conditions. And once we have those redundant forces numerically, we all we have to do next is just to solve a determinate structure. Now, as I said, that if there is a support reaction redundant, once you have that numerically, you can just treat it as an applied force, and you can solve the structure. And what does solving a structure entirely means? Entirely solving a truss means finding out all the member forces and finding out all the joint displacements. You won't be asked to calculate all this in a single question, but that is what solving a truss entirely means. So that brings us to the end of the class. Are there any questions? Okay, then I'll end the class. Next class we'll look at the how to apply the method of consistent deformation to frame structures.